This is a simple constant velocity problem in 2D. Mr. Crab here is on the beach moving towards the water at constant velocity. Here is the surf, and he's going to be moving along this path here towards the water with a speed of 6 centimeters per second at this angle. Now, if the direct distance to the water, this distance here, is 26 centimeters, how long will it be before Mr. Crab hits our water here? It's a simple problem, but I would like you to find the answer in two different ways. First, find the change in time by finding his path length, the length of this path here, d. And then the second way would be to find delta t by first finding the y component of his velocity. Let's draw in his velocity vector triangle. If his displacement is in this direction, his velocity will be parallel to it, so I could draw in a velocity vector like that, and draw the legs of that right triangle, and this angle will be the same as that angle. These will be similar triangles if he's moving at constant velocity this whole time. That leg is the y component of velocity, that leg is the x component. And the relationship between all these things is as follows. As long as v is constant, then our speed is just given as the distance over time, sort of a distance is rate times time scenario. And then in the x direction, the x component of velocity, delta x over delta t, and in the y direction, delta y over delta t. Okay, go ahead and pause the video, find delta t in those two ways, then we'll over it together. Ready? Okay, first way. Just set up a little trig problem, draw your triangle, and to find the distance traveled here, cosine of that angle is delta y over d, so rearrange to d is delta y over cosine theta, comes out to be 35 centimeters, this path here. Then once you know that, he's traveling in this direction at 6 centimeters per second, he's got to go those 35 centimeters, so we can rearrange this relationship to solve for the change in time, d over the magnitude of the velocity, also known as the speed. Substitute in this expression for d to get this, then plug our values in, comes out to be 5.8 seconds before it hits the water. The second method would be to look at his velocity triangle instead. The hypotenuse here is his speed, 6 centimeters per second. Cosine of the angle will be Vy over the speed. Rearrange that to solve for Vy, which would be V cos theta, comes out to be 4.5 centimeters per second. So if he's traveling in this direction at 6 centimeters per second, his y-coordinate is changing at 4.5 centimeters per second. And then knowing that, we'll use this relationship to solve for delta t, the change in his y-coordinate over the rate of change of the y-coordinate. But rate of change of y-coordinate, we can substitute in this expression here to come up with this. And this expression, we notice, is exactly the same as what we came up with right here. So when we put the numbers in, we'll of course get the same result, 5.8 seconds. So to recap, we can look at how long it takes him to travel this distance here at 6 centimeters per second, or we can look at how long it takes him to travel this distance, this vertical distance of 26 centimeters at that 4.5 centimeters per second. Okay.